Okay, welcome everyone to this week's IMP One World Mathematical Physics seminar. For those of you who might be joining us for the first time, this is the regular seminar series of IMP, International Association of Mathematical Physics. So if you want to find out more about our organization, you can check out the link posted in the chat, and you can also join our mailing list so you'll be informed about upcoming seminars. Now, let's go to the talk. So it's my great pleasure to welcome John Dimock here from the State University of New York at Buffalo, and he's going to talk about an ultraviolet stability bound for quantum electrodynamics in D=3. So this seminar, as all our seminars, is recorded, and you can watch it or rewatch it on our YouTube channel. And now, John, the floor is yours. Thank you.
Thank you, and thank you very much for inviting me. So the subject is quantum electrodynamics, that is quantum field theory for relativistic electrons and photons on a d-dimensional Euclidean space-time in general. And just a little orientation here. If d=2, that's what's called the Schwinger model. There are a great number of simplifications, and it's more or less completely solved. For d=3, you have both ultraviolet problems and infrared problems. That is, ultraviolet problems, short distance problems, infrared problems are long distance problems. This talk is about ultraviolet problems in d=3. As for infrared problems, there are some modest results, but really not much is known in there. And in d=4, the ultraviolet problems are a big difficulty because there's a lack of asymptotic freedom. That is, in the very short distances, the theory is not free, and it casts doubt on whether you can give a strict mathematical construction to it at all in its pure form. So that's still a quite open problem. Infrared problems should be more tractable because it is asymptotically free in the infrared. And the kind of methods that I'm discussing in this talk might also be applicable to infrared problems in d=4. Okay, so let's establish some notation. First of all, I'm starting out on a lattice because I want to preserve gauge invariance as much as possible. And the lattice regularization is the best way to preserve gauge invariance. So I'm going to be talking about toroidal lattices with spacing L⁻n and with size L⁻m, where n and m are possibly large integers. And in this talk, we're interested in the n go to infinity limit. So m is not important. We're just going to set m equal to 0. And we'll start with the lattice T0n, which has spacing L⁻n, which I also call epsilon, and it has a unit volume. So on this lattice, we have Fermi fields, psi and psi bar, at each point in the lattice. They have Dirac indices, and they're totally anti-commuting. So they're the generators of a Grassmann algebra. And we also have gauge fields, which are the electromagnetic potential. The gauge fields are defined on bonds. Bonds are a pair of nearest neighbors, x and x prime, in the lattice. And we're assuming A is antisymmetric in the points. Corresponding to the field, there is a field strength, dA, which is defined on plaquettes. Plaquettes are elementary squares in the lattice, and you just sum the bonds around the plaquette. And that gives you what is the electric and magnetic fields. you can think of the gauge fields as being one forms and the functions on plaquettes as being two forms, which is why this notation is used here. And then there's a coupling between the gauge fields and the Fermi fields, which is given by a covariant derivative in the lattice. So you take a point and you move away from it at one lattice point, and you subtract them and divide by epsilon. That's the derivative. But you first want to parallel translate at this point x plus epsilon e mu back to the point x. So you're subtracting things at the same point. And then the covariant Dirac operator is the some gamma matrices dot its covariant derivative. And then there's a correction due to Wilson, which is proportional to the lattice spacing and the covariant Laplacian here. And it's designed to give you the right continuum limit, at least formally. So that's what we'll be working with. And then there's an action. It's a function of the gauge field and the Fermi field. It's the sum of dA over all the plaquettes squared. There's a fermion term with the Dirac operator and a background mass m bar. And then there are counter terms which are going to depend on the lattice spacing, mn and epsilon n. This is the mass counter term, and this is energy density counter term. So from this action, you can form a partition function, which is the exponential of minus the action, integrated over all the gauge fields, all the Fermi fields. And this is Grossman integration, which means projection onto the highest element. So this partition function is going to be a function of the coupling strength E, which I forgot to emphasize back here in the covariant derivative. It's weighted by this coupling constant E, which is the elementary charge. So it depends on this coupling constant and on the lattice spacing.
May I ask a question?
Yes.
So in the action, how is the bracket between psi and psi bar defined?
It's just an inner product, a real inner product. It's the sum over, evaluate this at x, evaluate this at x, and then sum over all x.
But psi and psi bar are Grassmann valued functions.
Yes.
And do you just sum over Grassmann valued numbers? I mean A numbers instead of C numbers?
Yes.
So the action S is essentially a super number, right? Mixing of C number and A number.
Yeah, it's an element of the Grassmann algebra.
Then how is the exponential of S defined?
How is the exponential defined?
Oh,
It's defined by the power series.
but the power series does in what sense does the power series converge? Like in what norm?
In the there is a norm on the Grassmann algebra, which I'm going to mention later on, and in that norm it converges.
Okay.
Yes, those are quite relevant questions indeed.
And just one more. Are you assuming the Euclidean field theory instead of Minkowski? Because I do not see I here and I see just minus sign.
Yes, it's all Euclidean, and the idea is to worry about analytically continuing to real time once you get to a continuum theory, and later. I mean, that it's sort of a basic starting point. And in the far future, that's an issue to get back to Minkowski space, but we're confident that that part is not the hard part.
Okay.
Not that it's easy. But. So the theorem I want to talk about is ultraviolet stability, which says that if you have a positive mass, and if the charge is sufficiently small, you can choose the counter terms so that for all n, that is uniformly in the lattice spacing, the ratio of the partition function with the coupling to the partition function without the coupling is bounded above and below. And so it's a bound uniform in the lattice spacing. So this is supposed to be a first step towards the construction of the model in a finite volume, in this case, a finite torus. And it should be possible by these methods to also prove similar bounds on correlation functions. That is correlation function where you insert a lot of fields in this integral here instead of just the action. And also take the continuum limit, n goes to infinity.
By correlation functions, do you mean the Schwinger functions?
Yes.
Okay.
Exactly. Yes. So this result is contained in a series of papers, mostly in Journal Math Physics, the final one in Henri Poincaré, which has appeared in the last few years. And the result is based on earlier work by a lot of people, but mainly by Balaban. The methods I'm going to describe were almost entirely created by Balaban. And so I'm going to review some earlier work here. Balaban started things off by studying scalar QED in D equals 3, and he proved an ultraviolet stability bound, but he assumed a massive gauge field, that is massive photons, which changed the character of the problem somewhat, needless to say. And then a little later on, Balaban, Imbri, and Jaffe studied the abelian Higgs model in D equals 3. That's again scalar QED, but with a special potential for the scalar field, which was supposed to generate masses by the Higgs mechanism. And they got some interesting results, but it was never actually finished. And then Balaban, in the late 80s, studied pure Yang-Mills theory in D equals 3 and D equals 4. And this was just a masterful piece of work that spread over something like 10 papers. Unfortunately, it wasn't quite complete, at least in D equals 4. What's missing there is analysis of the beta function to second order perturbation theory. And it's not standard perturbation theory, it's a lattice perturbation theory, and it's not standard lattice perturbation theory, it's a special one adapted to its proof. So it's not something you could quote from somewhere else. And he just, I think, ran out of gas and just never finished it. But I think it's not a serious problem. I think his method for Yang-Mills is basically correct and can be completed.
Did he establish the mass gap in 3 dimensions? I don't remember him establishing the mass gap because I looked at those papers.
No, he did not.
Okay.
It was just a stability bound.
Okay.
Yeah. And then Balaban and O'Carroll and Shore started taking up fermions. And one of the main technical difficulties with fermions is you need to multi-scale lattice propagators in a way which I hope to get to in this later on in the talk. And they proved some technical results on those. And then more recently, I took up scalar QED again, now with massless gauge field, but I had a bounded field assumption, which still needs to be removed. So all in all, it's really just a bunch of partial results. Even Yang-Mills D equals 3 is technically a partial result, because although all the pieces are there, he never quite puts them together. If you try to read it, you may find it frustrating. All right, so now let's start in on the discussion of how this is proved. I started on this lattice with spacing L and -n. Now I scale up to a unit lattice with a large volume. Now the dimension is L to the n. And now the n goes to infinity limit is now an infrared problem rather than an ultraviolet problem. The partition function scales up, everything scales up, the action scales up. The action looks just like before, except that everything's on a unit lattice now. And the parameters have all shrunk. So the coupling constant is shrunk down by L to -n. The background mass, L to -n, the mass counter term, and the energy density by L to -3n. So the n goes to infinity limit is now an infinite volume problem, but with scaled parameters. This is just a convenience. You wouldn't have to do this. So the basic method is renormalization group transformations. And the idea is to use averaging operators to associate fields on the unit lattice to fields on a larger lattice with spacing L, an L lattice. And then you integrate over all fields on the unit lattice with fixed averages on the L lattice. And that generates a new action for fields on the L lattice. Then you take this action and you process it. You exhibit a local structure. As to be able to iterate this procedure, you have to keep track of a local structure for these actions. And you also want to isolate the leading terms, the biggest terms, in order to keep track of renormalization. And then finally, you scale back to a unit lattice. All that is one step, and then you repeat this over and over again. Each step reduces the number of variables and isolates the important terms. In fact, the basic problem is that you have too many variables. You have an unbounded number of variables, which makes it very hard to give estimates. And by this, you're integrating out some fields a little bit at a time and reducing it down to just a few variables where you can actually make good estimates.
So this is the Wilson scheme of renormalization, right?
The which scheme?
The Kenneth Wilson.
Oh, I'm not familiar with that. No, I don't know. I call it block averaging. Perhaps it is. I'm just not familiar with it.
Okay.
Yeah. Okay, so first block averaging for fermions. So you take a point on the L lattice, Y, and you have a field on the unit lattice, and you average over all points in a block of size L centered on Y. So that's this. You're summing over psi x, all points within a distance L over 2 of Y, and that's giving you this averaging operator Q. But first, you are parallel translating the field at X to the field at the center of the block, Y, with this parallel translation operator. And when you do that, it's gauge covariant. So if you make a gauge transformation with A and psi, then Q of A lambda psi lambda is QA of lambda 1, where that's the restriction of lambda to the larger L lattice. It's going to be important to preserve gauge invariance as much as possible throughout this process. So now here's a renormalization transformation with just fermions now. starting with some initial density of fermions, like e to the minus the action, defined for fermions on a unit lattice. You defined a new density on fermions on an L lattice, rho tilde psi 1, by an exponential of e to the minus psi 1 minus qa psi 0 squared rho 0, and then you integrate over all field psi 0. Now, this is not actually a square. This is that 2 there is just to remind you that this is a quadratic form. This is a shorthand I'm using for this quadratic form here. It's psi 1 minus qa psi 0, psi 1 bar minus q minus a psi 0 bar. The bars, the size and the sidebars are completely different. Now, this is, you would like to put a delta function here instead of this exponential. You would like to have a delta function which fixes the average of psi 0 to be equal to psi 1. But that's hard to do. In fact, it's actually been proved impossible to do with Grassmann variables. So that's why we have the exponential here. It's sort of an approximation to the delta function. It's suppressing variables for which psi 1 is not near q psi 0.
Excuse me, what is b?
B is just a constant.
Which will be kept constant, or which will be adjusted?
It's a constant which is the same in each step, but it'll, as you accumulate steps, it'll pile up to an adjustable constant. But in fact, it's not very important. It's always bounded above and below. L here is going to be assumed to be large. B is just order 1.
Can I call B the characteristic scale length of QED?
What do you mean?
The typical interaction scale of QED.
Yeah, well, I don't know that enters at this point.
Okay.
So, all right, so this is the transformation, and then you scale. So instead of psi 1 on the L lattice, you take psi 1 on the unit lattice, then you scale it up to the L lattice, and then you scale the density accordingly. And you choose the constant in this transformation here so that when you integrate over psi 1, it knocks out this exponential and just gives you the integral over psi 0. So the partition function, which was originally expressed in terms of the integral over rho 0, can now be computed as an integral of rho 1. And that's the basic idea, that you can now compute the partition function with fewer variables. Okay. So suppose you start with an initial density, which is this Dirac operator, and something else. In the first step, this would just be the counter terms, but in later steps, this would be some complicated function of psi 0. And so now you define this transformation, this averaging transformation, with this density. And what you have here in the exponential is a quadratic form in psi 1 and psi 0. And in order to process that integral, you would like to diagonalize that quadratic form. And diagonalizing the quadratic form means finding the critical points, finding the points where the derivative is 0, treating them as functions just for the moment. So you can easily compute the critical points of this in psi 0. And you find that the critical point psi 0 critical is some function psi 1 of A. It's a linear operator H0 on psi 1. And the linear operator is a certain operator S0, Q transpose, and then psi 1. And S0 is a Green's function for this problem. It's the Dirac operator plus Q transpose Q. And this Q transpose Q is a projection operator, it turns out. It's a projection onto the kernel of Q. And it has the effect of providing an effective mass for this Green's function. See, the problem here is this background mass has become very tiny, and it doesn't really function as a mass. But this projection operator acts as a mass and enables you to prove exponential decay of this Green's function. And so the upshot is that this critical field, psi 1, is some smeared out version of the fundamental field, psi 1, thanks to this exponential decay. And I should also say here that you can't always prove that this inverse exists if you just take an arbitrary A. You need some restrictions on A. And in particular, what you need is that the field strength be bounded in order for this to exist. So this is the first appearance of two themes here, which is that we're going to need bounds on the field strength. And we're going to need to keep track of these critical points of the action, which are going to keep popping up over and over again. So I said we want to diagonalize this quadratic form. So now we take the critical point and we take the deviation from the critical point. And instead of an integral over psi 0, we integrate over W0. The quadratic form splits, and the new density has a distorted fermion action, which looks like this. It's a function of the fundamental field psi 1 and the smeared field psi 1, which depends on the background A. I should have said A here is not dynamical. A is just some background field. But later it will be dynamical. And this distorted Dirac action is what you would expect here, but then this exponential distorts it. And then you have a fluctuation integral, which is a function of the new field. And it is f1 of psi 1 is the integral of f0 of psi 1 plus the fluctuation variable W0. And then this Dirac operator with projection here, dW0. And this is the form that is a Gaussian integral on the Grassmann algebra. And it's usually written like this: f0 psi 1a plus W0, and then this. It's not really a measure. It's the integral which makes sense, but if we write it as a measure, d mu S0, the Gaussian measure with covariance S0 in W0. And there's this normalization factor out front, Z0. So the effect of expanding around the critical point is we've been able to identify a fluctuation integral, which is a Gaussian integral. And now this is what we want to analyze. We want to see how this depends on psi 1 of A. And the issue is to keep track of the locality of in its dependence on psi1 array. In particular, we'd like to show that if F0 is localized in these fields, then after you do the integral, it's still localized in these fields, thanks to the exponential decay of this S0, which I mentioned before. All right, so here's some definitions, how we're going to impose the locality. A polymer X is a connected union of large blocks. These are bigger than the scale L, which is our basic scale. So some power of L. A polymer function is a function of polymers and fields in which the fields only depend on the only dependence on the field is in X. And then there'll be so this will be element of the Grassmann algebra. E sub H is a norm on the Grassmann algebra in which the fields are weighted by H. So the way this norm is defined, you just replace the elements of the Grassmann algebra are going to have kernels for each number of fields. And you take this kernel, you take the absolute value of the kernel, and then you, instead of the fields, you put in, instead of n fields, you put in h to the n. And well, I could write it down, but it would take a little digression here. So there is this natural norm on the Grassmann algebra. And now what we need to preserve the locality is a cluster expansion. So we assume that F0 is local. That is, it's the exponential of a sum of local pieces, local polymer functions. And it has a norm, these local pieces have a norm, which is bounded by a constant C, and then it's exponentially small in the size, in the number of elements in the polymer. X sub n is the number of M blocks in the polymer. So if C is small, then this fluctuation integral of the type I discussed is, whoops, this should be an F0 here, not an E0. It's F0 of X psi1a plus W0, and then integrated with this Gaussian. And the cluster expansion, which is a standard theorem, says that the result is the exponential of a sum of polymer functions of psi1 only, still with a small parameter and but slightly larger, and with a slightly worse decay rate. Okay, so that's going to be a basic tool. Now let's talk about block averaging for gauge fields. So again, we have a gauge field on a unit lattice, and we want to average over blocks on an L lattice centered on points Y.
I just have a question. Is that the cluster expansion in the same sense of what Glim, Jeffy, Spencer did in their construction of 5-4 theory in 3 dimensions?
Yes, it's one version of it. There are many different versions, but yes, it's the same basic idea.
Okay.
Yeah. So the average field is now going to be a function on bonds in the L lattice. So y plus L e. And to form this average, you pick a point in the unit lattice, and then you take a line integral, line sum, along a contour from that point to the associated point in the neighboring cube, so adding L e mu. And then you average over all initial points in the cube. And this is also designed to be gauge covariant. So if you take the average of A lambda, you get QA with the gauge transformation Q lambda, where Q is now an average of scalars. It's just a straight average. There's no line in it. So now the renormalization transformation is that you integrate over all unit lattice fields of some density with the requirement that the average be fixed to be some A1, and that gives you a new density tilde rho 1 of A1. And here I really can use a delta function. And then you scale like we did for fermions. But now there's a new problem, which is we're interested in initial densities of the form e to the minus dA0 squared times some function FA0, which is, for example, coming from fermions. But the F0 typically is gauge invariant and bounded. And that means this integral is not going to converge. It's because this dA has a large null space. It's not giving you decay in some direction. In fact, the whole thing is constant on gauge orbits. And so you're not going to be able to integrate over these gauge orbits. So the standard fix for this is you pick a point in each gauge orbit and integrate over that. So this is called gauge fixing, and we have to do that. And we will impose a certain kind of axial gauge. So I've added this extra term here, delta tau A0, which is enforcing the actual gauge. And the way it does this, it sets A0 equal to 0 on trees in each block. So here's a typical tree here, although this I've written in 2 dimensions. In 3 dimensions, it would look like this, but there'd be spikes coming in and out of the board as well. So it's not a global tree, it's just a tree in each L block. So we're taking advantage of this renormalization group method to avoid imposing a global gauge. Employing a global gauge causes problems, whatever kind of gauge you try to put in. And here we're just doing it a piece at a time. The effect is when you add this axial gauge on these blocks, and you repeat this over and over again, it gives you sort of a hierarchical gauge fixing, which works out nicely. So you justify this by a Faddeev-Popov argument. And now with these 2 delta functions here, this dA squared is positive definite. And so this integral is going to converge. So it's doing its job. Neither one by itself is sufficient, but together they do it.
Do you have enough freedom of choice, degrees of freedom to choose a specific gauge you want?
I can choose different gauges. I'm not, what do you mean by that?
Oh, I see. It's not a continuum theory. I see. Okay. But axial gauge seems to destroy the Euclidean covariance in the sense of axial gauge destroys the Lorentz covariance in relativistic field theory.
Yes, that's an excellent point. For one thing, I seem to have chosen a special orientation for this tree here.
Yes.
And that would destroy Euclidean invariance. However, what you do is you average over the orientation of the tree. And so that's not a problem. And,
I see.
Yeah. And because your new density doesn't see the details of this averaging here. And you still have Euclidean invariance in the new density.
Wow, that's interesting. I see.
Yeah. All right, again, we try to, we have a quadratic form. Well, the quadratic form is dA squared, but we're interested in dA squared restricted to this subspace here. And we would like to expand around the minimizer of that. So that's what I'm calling A0 critical. It's a linear function of the fundamental variable A1, the minimizer of dA squared, subject to these two constraints given by the delta function. So we call script A1 this critical field. And we make a change of variables expanding around the critical point. It splits the quadratic form. And we find that the new density is e to the minus dA1 squared times a fluctuation interval again. The fluctuation integral turns out to be delta QZ0, delta tau Z0, e to the minus dZ0 squared, which again is positive definite. And then whatever density you started with at this translated field. And again, we would like to make a cluster expansion. So if F0 is a sum of polymer functions, can you conclude also that F1 is a sum of polymer functions? And the answer is yes, if E0 is small. And that's going to be true in this model if the coupling constant E0 is small, which is certainly true. But now there's a problem with the fields that wasn't present with the fermions. I mean, the fermions are essentially bounded. They're bounded fields. The gauge fields are not bounded. And even though E0 is small, E0 times these fields could be large. So you need a condition on the size of the gauge fields. And what turns out to be a useful choice is that the dA1 and Z0 should be bounded by some function of the coupling constant, E0, proportional to a power of the log. Okay, so it's the log of E0 inverse to P. E0 is very small. E0 inverse is very big, and raising it to the power P is big, but it's still not so big that it makes E0 times dA or E0 times Z0 big. They stay small. That's why this is a good choice. And the expectation is that introducing these bounds will induce a small error. Because of these, well, like for dA here, this factor up here, e to the minus dA1 squared, is strongly suppressing large values of dA. Okay, more about that later. Let me mention other gauges, because other gauges are also going to be important in this. There are covariant gauges defined as follows, for some real number alpha, and for delta, which is the transpose or the adjoint of this D operator. It's the divergence. Delta of A is the divergence. And instead of the axial gauge delta function, you have this factor e to the minus 1 over 2 alpha R0 delta A0. That's the divergence of A0. R0 here is a projection operator. It's the projection onto the Laplacian on the kernel of Q. Let me come back to that R0 in a minute. There's also a Landau gauge in which you let alpha go to 0 and makes this into a delta function. So it's So it's delta R0, A0 now, which is replacing the axial gauge fixing here. These are all equivalent to the axial gauge by Faddeev-Popov arguments. So this requires a little argument, but it's true. So I could work with these gauges as well. Now, why is that R0 there? It's because when you make this Faddeev-Popov argument, you have to make a gauge transformation to a field in which the divergence is 0. But you have to respect these delta functions out here, and you want them to be unchanged. So it turns out that you can only accomplish that if you take special gauge transformations which have the property that the average of lambda over the block is 0. And with these special restricted gauge transformations, you cannot get to just pure dA0 or delta A0. This projection operator pops up. And it's unfortunate because if you didn't have this projection operator, this would be the Laplacian, right, here, as a quadratic form, and that would be much easier to deal with. This projection operator is somewhat non-local and causes some angst. But anyway, there it is. All right, so now let's back to the main problem. So we're starting with a density, which is a function of both fields. It's e to the minus the action, A0 psi 0, and this is on a large unit lattice again. And we define a sequence of densities on smaller lattices by first taking block averages in fermions and in gauge field with axial gauge fixing, with some characteristic functions here, which limit the size of the fields, both AK and A1, and then the density rho K. And these characteristic functions are going to use PEK bounds. Those are logarithmic in EK inverse. And by putting that in, I'm not solving the real problem. So I have to show eventually that I make a small error in putting in these characteristic functions. But for the time being, I'm just going to iterate this renormalization group with these characteristic functions. Hence the title RG with bounds. And at the end, I'll say some words about how to remove the assumption here. But we've seen in two separate places where it was important to have bounds on A. You need these bounds to analyze this. And then you scale as before. And so you get a sequence of densities. At each step, you expand around critical fields in AK and psi K. And the results are naturally expressed in terms of K-step critical fields. These are critical fields that you would get if you repeated the block averaging K times and then took, at that point, computed critical points. So they are both linear functions of the fundamental variables, AK and psi K. And they themselves live on an increasingly fine lattice, an L to the minus K lattice. And they're given by these linear operators. Okay, so these critical fields are smeared out versions of the fundamental fields. And it's in terms of these critical fields that our action is going to be expressed. Now, there's going to be a problem there, which is that the axial minimizer is not smooth. well, in some sense, everything is smooth since we're on a lattice. But when I say it's not smooth, I mean the bounds on the derivative are not uniform in the lattice spacing. It's not smooth. This is a well-known difficulty with axial gauge. There's bad ultraviolet problems. But the covariant or the Landau minimizer, which is, I write like this AK is HK, AK, is smooth. In fact, it turns out they're the same. Both, all the covariant and the Landau minimizers are all the same. Is somewhat smooth. They have derivatives of order up to 2, not including 2, but fractional derivatives right up to 2. And it's gauge equivalent to the axial minimizer. So in a gauge invariant setting, you can replace your axial minimizer by this Landau minimizer. And you can get much better estimates. So the overall picture is the basic gauge is this hierarchical axial gauge. But when we need detailed estimates of short distance behavior, we just switch over in special places to these Landau gauges. So after k steps, you expect to get the following standard form. The density is a function of the fundamental fields AK and psi k, normalization factors, e to the minus dA squared, and this A, everything here is evaluated at this critical A field, the critical minimizer. Then this distorted Dirac action, counter terms here, which have evolved in a way that I'll explain in a minute. And then everything else is thrown into a polymer function, which is expressed in these critical fields again. See, the idea is if you try to track how these densities evolve in the fundamental fields, you rapidly get lost. But they keep a very nice form in terms of these critical fields, which themselves are functions of the fundamental fields. The coupling constant has scaled up by factor L to the K over 2. The masses have scaled up by a factor L to the K. So that's what's appearing in this distorted Dirac operator here. And this one of these normalization functions is going to be important. It's actually a function of A. And it's the determinant of this Dirac operator with projection here. Although it does not appear with an A here. We have to remove the A and make it a 0 for technical reasons. Okay, important point. Everything here is gauge invariant and covariant under lattice symmetries. And we've gone to a lot of trouble to preserve those properties. And in particular, there's no photon mass term, which might have been generated as we iterate this process. But because it's not gauge invariant, it just doesn't occur. All right, so here's the basic theorem for one step. It says, suppose EK is sufficiently small. And suppose for bounded DAK, rho K has the standard form, which I just wrote down, with MK less than or equal to 1, and with the weight function, some inverse power of the running coupling constant. So this is a big number. And suppose the following norm, supremum over polymers, supremum over A bounded, I haven't indicated that, there's a bound on A here. With this fermion weighting function, with this decay here, should be less than 1. this is actually demanding that E be very small, because I have these large factors here, this HK and this exponential of XM. And to compensate that and make this less than 1, this actually has to be quite small, so that the smallness is hidden there. Okay. If all that is true, then rho k plus 1 also has the standard form for bounded dA, with the parameters evolving as follows. The energy density, you take the old energy density and you add a correction and then scale. For the mass, you take the old mass, add a correction, and then scale. And then for the polymer function, you have the old polymer function. You apply a linear operator R, which removes the relevant parts from this polymer function, and transfers them to these terms here, this E star and this M star. Those are the most relevant parts of EK, and they're gone now. And then you add to that a correction, which is what's generated at that step by all the other terms in the action. And then you scale that with an operator L, which not only scales, but it reblocks to a larger number of blocks. And things are arranged so that E does not grow. The polymer function does not grow. EK plus 1 and K plus 1, which is less than these two. Because you remove the relevant parts of E, scaling, which ordinarily would increase things by L cubed, actually decreases things by the way it's set up by L to minus 1/4. And then all these contributions to E star are small. Turns out order EK to the 1/4. And then the L cubed is beaten by the EK to the 1/4. So these are both small numbers, and it's still less than 1. So the E is not growing. The whole problem is now, the problem is you have to analyze the flow of these equations. And the danger is that they'll grow too fast, that they'll blow up. And the way the theorem is set up, the most complicated term, the polymer functions, are not going to blow up. All the possibility of blow up is in these E star and this M star. And the idea is that you should pick initial conditions for the E and M so that it doesn't happen. Okay, this is renormalization, non-perturbative renormalization. It says, there is a solution for which doesn't blow up. So it says there exists a unique bounded solution of those flow equations defined for all k up to n with arbitrary final conditions, which I've arbitrarily taken to be 0, but you could take any small number here. And with the initial polymer function equal to 0, because that's the model. With those boundary conditions, so there's an initial condition, or there's a final condition and an initial condition. With those boundary conditions, there's a unique solution, and they're all small by certain powers of the coupling constant. And so remember, EK here is growing, but E0 started at L to minus N. So these EK is actually L to minus N minus K over 2E. So at N, we're back to our original coupling constant, E. So that's the theorem. The way to prove this is as follows. The energy density evolves separately. It doesn't couple back to the mass in the polymer function. So we can ignore that. Just think about the mass. Formerly, we had the mass k plus 1 was L times mk plus m star. Just turn that around so mk is expressed in terms of mk plus 1, L inverse mk plus 1, minus m star. And here is the same equation for the flow of E. Okay, so with M, it's depending on k plus 1. With E, it's depending on k minus 1. And because we're talking about the entire sequence, it suffices to study this. And in fact, in the space of sequences, MK, EK, satisfying the boundary conditions, this has the form of a fixed point equation. That is, this T, it has the form C equals TC, where T is the operator on the right side of this equation on sequences. And C is just the sequence. So it's a fixed point equation. If you can show that it's a contraction in a suitable norm, you can quote a fixed point theorem and get the result. We've already seen that E is contracting. And because of the way we rearranged the M equation, it's now contracting because of this L inverse. Okay, so there's a substantial argument here, but that's the basic idea. This kind of argument that I'm giving here, this renormalization as a fixed point problem, should work for any super renormalizing theory like this one. Well, I see I'm running out of time, but I just say a few words about the full renormalization group. So now we don't put in the characteristic functions by hand.
Sure, yeah.
Yes? We don't put in the characteristic functions by hand.
I should just go ahead. Yeah, we can go a bit. Yeah.
Okay. So this is the true model now. The density after one step is given by an expression like this. Now we insert characteristic functions as follows. Chi is a certain characteristic function limiting the size of fields in an M cube. And I've defined it down here. What turns out to be needed is dA0 less than P of E0 and A minus A critical less than P of E0. Zeta is 1 minus chi, so they sum up to 1, so the product is 1. And then you expand out this product and you get sum over regions, chi omega, zeta omega complement, which are products of the characteristic functions of the cubes. And so you insert that at each step. This is the first step. You insert it at each step. Now, in the small field region, the earlier analysis holds. In the large field region, if large field region, there were two conditions. Suppose there's just one, that dA0 be greater than P0. Then this characteristic function times the e to the minus dA squared, you can extract a factor e to the minus PE0 and still have half of this left. Then you take the product over cubes, and this, you get a factor like this. And in particular, this is strongly decreasing in the number of cubes in the large field region omega complement. That's going to make it possible to sum over the large field regions. And furthermore, this factor is very small. It's smaller than any power of coupling constant to n0. And it's going to mean that the contribution of the large field region is very tiny. And it's dwarfed by the contribution of the small field region. So in particular, it does not need renormalization at all. Well, all right, I better just skip over this, but after k steps, you get a monster expression for the density. And because of the care you've taken that things don't grow, when you get down to almost n, you have something that, although it's very complicated, has nice estimates, and and you can prove the stability bound. So, well, here I've defined some of those terms there. And one last remark is that what's technically a very difficult part of this is that you have to keep track of the localization of these critical fields. And that means you have to be able to break up these minimizing operators, or these critical operators. And these have a certain multi-scale structure, which I haven't been able to go into very much. But to analyze these, you need to construct multi-scale random walk expansions, which are fairly complicated. It's one of the technically most difficult part of the group. But I better stop there.
Okay, thank you very much for this very nice talk.
Thank you.
So are there any more questions?
This is a fundamental question. There are some fundamental questions, but so I am aware that Arthur Jeffrey has already written a paper on the reflection positivity of QED. So combined with the paper, is it possible to pass to Minkowski spacetime?
No, you would have to take the continuum limit first, and then you would have to take the infinite volume limit as well.
But with your estimates, isn't it possible to take the? Oh, I see. It's not the.
This is still ultraviolet control. So,
right.
And not yet correlation functions.
Yeah, there's that too. I think the continuum limit is quite feasible. Once you have uniform bounds.
Can I ask a question? So, yes, I have been puzzled by this critical field A, curly A. So, yeah, and you said that it's a very difficult part, which was hidden in this talk. So this is nothing which I can see explicitly, right? So this curly A is defined in a very, very complicated manner. Is that?
Yeah, let me just back up to say one thing about that. When you keep at each step, you're creating a new small field region, and so you get a sequence of small field regions, which are shrinking. And because you keep scaling things, the jth small field region is a union of steadily larger blocks. So you're shrinking down these regions and the blocks are getting larger. And this is where that multi-scale structure is coming from. Because yeah, if I can back up here to this, yeah, here to these Green's functions here. See, this was the initial critical operator,
Hmm.
which involved this Green's function with this projection operator. In this multi-scale setting, this projection operator has a multi-scale structure.
Hmm.
And that's what gives a multi-scale structure to these minimizers.
Hmm.
So one entire paper is devoted to these multi-scale random walk expansions.
Okay. Uh-huh. Hmm. The other sorry, the other question is about large field problem. And I thought the treatment of large field would be the hardest part in renormalization group method, which I always hear from like people like Kavitsky, Kupian, and Brickman. But do you say that in this case, large field region is not really a headache? You can treat it by simple combinatorial estimate?
Well, yes and no. I mean, basic concept is quite simple, but actually carrying out the estimates is very complicated.
Okay, everything is hidden. Mhm. Mm.
Okay, this is a more fundamental question, but have you heard of Epstein-Glaser renormalization as well?
Say it again.
Epstein-Glaser renormalization or causal perturbation theory?
Oh, yes, I've heard of it. Yes.
If we're satisfied with perturbative expansion of the S matrix, then it is possible to construct QED on 4-dimensional Minkowski spacetime without any problem.
Yeah, but I think that's not really the point, right? So we want to have something non-perturbative.
And this construction does not see, is this construction entirely non-perturbative?
Sure.
Yes.
Of course, you're using, yeah, sure.
Sure. Right. That's the whole point. Yeah. I mean, you do make expansions in the coupling constant, but it's just expansions to first or second order. It's never
Yeah.
to all orders.
So suppose the gauge group is non-abelian.
So what
Then-
about Young-Mills theories?
Yeah, then does it become much harder or just a little harder?
Yes, much harder. For one thing, you cannot deal with the fields directly. You have to take group valued fields and then exhibit the quantum fields as behavior near the identity. And I mean, if you start reading Balaban's papers, you rapidly see that it's much harder.
So just to follow up on this, I mean, what is the status of that? So Balaban's work and what would you say we actually can call a proven and what's still conjectural in that regard?
Well, I would say that in 3 dimensions, all the pieces are there, but they're not quite put together.
Mm-hmm.
And in 4 dimensions, there's a gap, which I mentioned, that the beta function to second order perturbation theory has to be analyzed.
Mm-hmm.
And I can't imagine it's serious, but it's a lot of work and nobody's done it. In particular, Balaban hasn't done it.
I see.
I mean, there were some competitors to Balaban, Rivasson, Magnin, and I remember listening to a lecture by Rivasson where he claimed that that he knows how to prove the stability of Young mills in 4 dimensions. So essentially, what is? I mean, could you comment on this?
Well, they say they know how to do it, but they don't do it. So
Okay.
to make of it, I think, often you think you know how to do something, but when you come to actually doing it, you run into problems, and so I'm skeptical.
But you believe it's doable, right? I mean that this.
I believe Balaban's proof is basically correct. Yes, and I believe that the gap is not serious, but it's a lot of work and nobody's doing it.
Well, yes, that's not making it done. That's it. Right.
Yeah, but Balaban considered only finite volume, and so do you.
So we are talking only about finite volume, I guess.
Yeah. So John, you're hopeful only about the finite volume thing.
Yes, right. Infinite volume is a whole nother problem. Yeah. That's the $1 million problem.
And nobody's working on it.
Well, successfully.
Successfully. No, but it would be great if we could actually have the full story in finite volume. That would really.
Yeah. Well, I'm tempted to work on it from time to time, but we'll see.
It's a bit of advertising now. Everybody watching us, there is a problem. Needs solving.
So
Yeah.
let me clarify. So what you want to do with all these uniform bounds is to construct a measure on the continuum in the continuum, finite volume, right? Path integral measure.
Yes.
With certain covariance properties, and then with some other properties such as the mass gap, you want to expand the theory to the entire R4 or R3 or R4 or whatever, right?
Well, except there's not going to be a mass gap just because of the massless photons.
Well,
Unless you put in a Higgs mechanism somehow.
yes. Yes, I was thinking of more of Yang-Mills theory. Okay.
Yeah.
All right. Are there any other questions that need immediate answer?
Maybe could you describe the remaining steps that you think could be done to finish the project just about the abelian fields in dimension 3?
In infinite volume.
If you insist.
Well, I think the methods I've discussed are sufficient to analyze the correlation functions, that is, give uniform bounds on the correlation functions, and to take the continuum limit. Yeah, so I think, although it's still a lot of work, I think you could get a continuum theory in finite volume. Then
Euclidean theory.
Yes, Euclidean theory, right. Right, of course, you want the infinite volume limit. and there's the problem with the massless photons.
Mm.
And it's now, I know that if you integrate out the fermions and just get an effective gauge theory, then you can analyze that by renormalization group. And it is, once the fermions are integrated out, it is asymptotically free in the infrared. And so you could take a limit there. But if you leave the fermions in, I think it's a problem. Infinite power limit.
I see. Uh-huh.
Yeah,
Okay.
so it's still a long way from getting a Minkowski space theorem.
Right. Mm-hmm.
And does your estimate depend critically on the dimension 3?
Yes,
Yes.
yes.
Because I forgot some of details. In what sense does your estimate depend on dimension 3?
Super renormalizability, yes.
Well, if I were in dimension 4, then I would have to track the coupling constant as well, besides the mass, right? And I would get coupling constant flow that was not asymptotically free, and I wouldn't know what to do with it. And things would be even worse in higher dimensions.
Mm-hmm.
In dimension 3, the coupling constant has a dimension, right? Because it's super renormalizable.
Correct.
Then
Yes.
how can you take the logarithm of the coupling constant directly without any what should I say, dividing parameter?
Well, it's because it's super renormalizable. I can just scale it. I don't have to keep track of corrections.
Mm-hmm.
What I mean is that you chose the norms of some functions to be inverse power of a logarithm of a coupling constant.
Yeah.
And in the logarithm, the coupling constant has a dimension, and you just take the logarithm of it.
Yes.
And is it possible to do it because the coupling constant carries a dimension itself, and the logarithm is defined in terms of power series?
Well, you never scale that that expression P and EK. You just replace it by new ones. So it's, I mean, the dimension isn't really a problem since you never scale it.
So maybe we could continue this discussion after the official end. It's getting a bit late. So maybe let's thank John again for this very enlightening talk.
Thank you.
And